So let me now discuss the free particle and its evolution and some general properties of evolution of solutions of the Schrodinger equation. So in classical mechanics, the sum of the kinetic energy and the potential energy is called the Hamiltonian function. So in classical mechanics, it's called H, and it has a kinetic energy plus the potential energy. So one must distinguish between the Hamiltonian function and the energy. The Hamiltonian function is the functional form of the energy, whereas the energy is a particular value of the Hamiltonian. So, in the previous segment, I was talking about how you can have operators in quantum mechanics. The observables are operators. And because an energy is going to be an observable in quantum mechanics, so we should have an operator which is associated with the energy. And this operator is called the Hamiltonian operator, and it's usually denoted by H hat. And it's given in terms of the momentum operators and the position operator in this way. So you might wonder what this thing is. So what this is that classically you might have some potential. Say the potential could be a harmonic oscillator potential, say half times some omega squared or something. I don't know if the mass, okay, let's call it K times x squared. Then in quantum mechanics, this will become half times K x hat squared. So for the Schrodinger equation can be written as the Hamiltonian operator acting on my wave function psi, and then that's given by I h bar d psi by dt. And this, this Schrodinger equation is a general equation, and the particular form that it will have will depend on whether we are using the position representation or the momentum representation. So mostly in this course, we will be using the position representation. So in most of the cases, this equation will look like the momentum operator is going to be given by this, and the potential energy operator is just the v of x, and right. So let us now specialize to the free particle in one dimension. And so our Schrodinger equation, let me rewrite it, is given by h squared by 2m, and then del squared psi by del x squared. And we also already saw that the solution to this equation is given by psi is equal to some normalization times e to the power I by h bar px minus et. Now this is an example of a function that is not normalizable, because if I take the mod squared of this thing, this is just a constant, because this guy is just a phase. So if I integrate this over all space, this is going to blow up. And therefore, this is an example of a wave function that is not normalizable. By convention, the normalization constant that is used for this wave function is 1 over square root of 2 pi h bar. So we can plug this into our Schrodinger equation, and as a result, we have that the energy is given by the momentum p squared by 2m. So solving this, we see that the energy is positive, but the momentum can be either positive or negative. So we have qualitatively two different kinds of solution for the free particle. And one of the solution will be 2 pi h bar e to the power I by h bar square root of 2me, which is a positive number, times x minus et, and the other one will be 1 over square root of 2 pi h bar e to the power minus I by h bar, and here it'll be square root of 2me x plus et. So this thing is a right moving plane wave, and this is a left moving plane wave. Now in classical mechanics, if you have a wave equation, we can have, say, a left moving plane wave or a right moving plane wave. We can have some standing waves, which would be kind of a, which would be a kind of a linear position. But here, these wave functions are representing, in quantum mechanics, these wave functions are representing particles. So what does it mean to have a superposition of these things? So according to quantum mechanics, which is a linear theory, this guy is also a solution to the wave equation. So we have some alpha, some complex number, and a wave which is moving to the left, plus beta times a wave which is moving to the left. So according to quantum mechanics, this is also a completely well-defined solution. But of course, it cannot represent a standing wave, so to speak, because if you observe the particle, we can see that the particle is either going left or right if you observe the momentum of the particle, right? So these are the new aspects that we have about quantum mechanics. Now let us next consider how the free particle evolves in time. So consider the Schrodinger equation again. So I h bar d psi by dt is h of psi, and so this is a first order differential equation in terms of time, and it's easy to verify that a solution of this equation is given by I x of t e to the power minus I by h bar, h, the Hamiltonian, let me put a caret on it to denote the fact it's an operator, times t, psi acting on x at some time t0. Now what is this object? This object is a formal power series. So this thing is going to be given by this sum. This is the definition of this object. There should be a minus here. Yeah. All right. So for the free particle, it's easy to see that psi of x of t will be given by e to the power minus I h bar, the energy E times t acting on psi of x of 0. So if I give you the value of the wave function at some time t0 over all space, we can find out the value of the wave function in the future just by multiplying this thing. And this only works when we have a free particle. So what we should do is that we should use the Fourier integral theorem. So if you use the Fourier integral theorem, then I have a double integral, and then I have psi of x prime 0 e to the power I by h bar p x minus x prime, and then I have dp dx prime. So now if I use this expression for psi x0 in this equation, and then I have a new expression for psi of x of t in terms of psi of x prime at time 0, and that's given by 1 over 2 pi h bar double integral e to the power I by h bar p x minus x prime, and then I have e to the power minus I by h bar. Now the energy is p squared by 2m times t, and then we have dp, and we have psi of x prime of 0 dx prime. So this thing, what we can do now is that we can now do the p integral, and this is not a difficult integral, it's just an extension of the Gaussian integral. And if you do that, we can write this equation as an object which we are going to call the propagator, and what it does, it takes a solution at an earlier time to a solution at later time. So the solution at earlier time was psi of x prime 0, and the later time is psi of x of t. And what it does is that it integrates this earlier solution over all of space, and it gives you the solution at a later time in all of space. So the graphical interpretation of this is that we have all of space here, and let's and this is given at some time, say t0, and in some future time, say t, we want to know what the wave function is over here at this value of x. So so this is all of x, this is x prime, and this is x. So to predict what the value of this wave function is here, what we need to do is that we need to know the wave function over all of space at a previous time, and that each part is propagated forward in time by this guy, this function, and that whole thing is integrated over with the weight of this thing. Okay, so this is the interpretation of the propagator. So I haven't given you the expression for the free particle yet. So let me give you the expression, which you can derive very easily by using the Gaussian integral techniques that I will show maybe in the next lecture. This is going to be given by m over 2 pi h bar it. So I encourage you to derive this, but this will also be provided in a future lecture. So again, let me just remind you, U is called the propagator. It is also called, especially the form where EH, this form, it's called the time evolution operator. And mathematicians call it the Green's function.